Welcome to the Isabel Bader Center for the Performing Arts at Queen's University. We wish to acknowledge the land on which the Isabel and Queens are situated. For thousands of years, it has been the traditional land of the Haudenosaunee and the Anishinaabe. Today, this meeting place is still the home to many Indigenous peoples from across Turtle Island. We are grateful to have the opportunity to live, work, and create on this land. Please take a moment to identify the emergency exits nearest to you. The use of any photography or recording devices is strictly prohibited out of respect for the performers. Thank you, and enjoy the performance.
Good morning. My name is John Burge, and I'm now a professor emeritus and retired Dan School of Drama and Music professor at Queen's University. And in 2015, I was asked by the provost of Queen's University at the time, Alan Harrison, to see if I could come up with some kind of musical tribute to the momentous announcement that Art McDonald had won the Nobel Prize for Physics. And I must tell you that I've had many phone calls sitting in my office over 38 years, and that was probably one of the most unexpected. But what I would say is that I think that phone call alone is a good indication of what makes Queen's University special, in that the connection of all the departments and all the sciences and all the arts and the community that exists here is really quite extraordinary. Also, if you've lived in Kingston for any amount of time, you'll know that it really is a small town. And so as soon as I got that phone call, I knew I had to write a piece for solo piano because Art's wonderful wife, Janet McDonald, was a piano teacher in Kingston for many years who had just retired, and we were both members of the Ontario Registered Music Teachers Association in Kingston. Even more closely connected than that is that organization. Every sort of June, the group would get together for a dinner, and Art, as anyone will know, is incredibly supportive and very connected to his family, and Art would go to those dinners. And invariably, we were the only two men at these meetings, and we knew each other because our offices are actually just a couple of buildings apart at Queen's, and we would sit together and have dinner. It was really quite wonderful. And so writing a piano piece seemed just absolutely perfect. When the Advancement Office, and I just want to give a real good plug to the Queen's Advancement Office because there's a lot of people coming here today from homecoming and are past supporters, current supporters of Queen's University. But when the Advancement Office heard that I had written this piano piece, they immediately set up or included it, my piece, as a dinner for some important donors that they'd set up in Toronto. So in fact, in April 2016, I premiered this piece at a really nice club on a beautiful piano in Toronto, and Art and Janet were there, and they had no idea that I'd written the piece. Really good surprise. The planning behind that was really quite extraordinary. Over the next couple of years, the Advancement Office put together a kind of roadshow where Art would go and talk about his science and Queen's and the SNOLAB, and I would be the warm-up act. I would go and play and talk about music and how the arts is connected to so many things. And I mention that because Art is an unbelievably resourceful, energetic person. And as a figurehead, you just can't imagine a better person to actually lead and go and talk about what has to take place in order to fund the sciences and make research happen. Okay, so that's sort of the background, but how do I write the notes? So you'll hear in my piece that I use the piano to create overlapping textures. In my mind, what they're doing is they're neutrinos that are traveling across the universe and bumping into each other or hitting something and changing color. So you hear the piano change colors. But at a deeper level, and I'll say the piece only takes about 8 minutes if you're pacing yourself, so you'll know what to expect. At a deeper level, though, this piece keeps becoming romantic. Romantic in the sense that, well, two things really. And I don't want to give you too much symbolism. I mean, you can hear the notes and zone out and do whatever you need to do to get through the next 8 minutes. But I hear two things. One, the love that anyone brings to something that they're so passionate about. I mean, you simply can't be a scientist at the level that Art McDonald and everyone involved with the SNOLAB and all of that research, undertook and successfully produced, unless you are so dedicated you're willing to sacrifice almost anything. Because you don't get there without setbacks and having to go back and redo grant applications and just try to make things work. So I hope you'll hear that dedication that any expert in their field brings to their area of research. But the second thing, and this piece is dedicated to Art and Janet, is the love that one gets from the support of their family. And that when things aren't going right, it's really good to have someone to talk to. Enjoy.
Wow. The power and possibility of human creativity and ingenuity, the coming together of art and science, such a fitting start to today's formal celebration. So thank you so very much, John. Maybe one more round of applause so I can compose myself. Good morning, everyone. My name is Nancy Ross. I have the privilege of being the Vice Principal Research at Queen's University. It's such an honor to welcome all of you here today. This is a very special event in the life of the university, and it is taking place in an exquisite building, the Isabel Bader Center for the Performing Arts. As we come together today, we acknowledge that Queen's University is situated on the traditional territory of the Anishinaabe and the Haudenosaunee peoples. We honor and thank the Indigenous peoples of this land and also recognize the lands across Canada on which we have the privilege of conducting research and working on science. What a pleasure to see so many people here today. So many members of the Queen's and Canadian research community are here. This includes faculty, staff, and students and alum from the Department of Physics, Engineering, Physics, and Astronomy. And for those not in the know, that is one department. And also faculty, staff, and students from across the university. I see faces from all corners of the university here. Research partners from across Canada are here. We, including SNOLAB folks, have come down from Sudbury, and the McDonald Institute Advisory Board came in person last evening. We had a delightful dinner out together. They're all here today to support and celebrate. The Queen's Chancellor is here. Hi, Sheila, I think I see you. Hi. And our board chair, David Court. Hi, David. Thank you so much for being here. Community members being here also make this so special as we celebrate a university that welcomes the community in and tries to be relevant every day for the community it serves. Your presence here makes this celebration that much more special, that much more momentous. Today, we are here to honor two significant milestones in the history of Queen's University and Canadian science: the 10-year anniversary of Dr. Arthur B. McDonald's receipt of the Nobel Prize in Physics, and the recognition of a major investment of $45.5 million to the Arthur B. McDonald Canadian Astroparticle Physics Research Institute. That's probably the only time you'll ever hear it spoken that way. The McDonald Institute, or MI. So these two major significant milestones. Before we begin with the formal program, I'd like to take a moment to thank John again to start our day. And it's a pleasure also to recognize these milestones during Queen's homecoming. It's homecoming weekend here today. There is yes. Physics, football, and fun do coexist. There's a palpable energy on campus as we welcome back our alum whose lasting connection to the university is a special feature of Queen's. It strengthens our community. It inspires future generations as well. We're delighted to have so many of you with us here today and to make this part of homecoming. Today's program and speakers will highlight not only the scientific breakthroughs made possible by the leadership of Dr. McDonald and the McDonald Institute, but also the broader impact of the investment of fundamental physics research, from the development of vital talent to the fostering of Canadian and international collaborations that push the boundaries of our understanding of the universe. This foundational research helps us to better know ourselves and is part of building a technologically advanced society. It's important also to recognize that the McDonald Institute, SNOLAB, and Queen's Department of Physics have been foundational in training literally hundreds of highly qualified personnel. These are young people who are comfortable with frustration and failure. They work on a frontier, and what a powerful thing to bring to any economy, any labor force of any nation. Many of these folks have gone on to work across the globe, whether it's in academia, but many are in industry, also in government and other sectors. This tremendous human capital demonstrates the profound and far-reaching benefits of investing in physics and physics research. With that, please join me in welcoming Dr. Patrick Dean, our Principal and Vice Chancellor, who is going to share some remarks on behalf of the university.
Good morning, everyone. Thank you very much, Nancy. I'm still musing on the complex interactions between physics, football, and fun. It's delightful to be with you all here today to celebrate two milestones, two great achievements which speak to the very heart of what our university represents, the spirit of discovery, of collaboration, and leadership in advancing knowledge. This is the kind of moment that reminds us not only of past triumph, but also of the limitless potential that lies ahead when vision, collaboration, and support come together, particularly in the field of research. Research impact is one of the goals of Queen's University. It is a pillar that defines who we are as an institution, and it informs our teaching and learning, it inspires our students, and drives innovation that has local, national, and global impact. Our university community is in the process of thinking ahead towards Queen's bicentennial in 2041. And as we think about that period that lies ahead of us, research will remain at the center of how we define our purpose and our contribution to the world. The work of Dr. McDonald and of the McDonald Institute, represented here by its scientific director, Tony Nobel, are powerful examples of this, in which curiosity-driven inquiry expands our understanding of the universe while simultaneously training the next generation of scientists and scholars, as you heard Nancy describe. Queen's has a proud and a long-standing position as a leader and facilitator of big science in Canada. From neutrino and dark matter research to major advancements in cancer and beyond, we have consistently brought together universities, government, and international partners to face and deal with some of the most profound scientific questions of our time. These efforts exemplify what is possible when institutions like Queen's act as conveners, connecting ideas, expertise, and resources across the country and around the world. So our institutional leadership in physics is not only a point of pride, it is also a national asset. The Nobel Prize was awarded 10 years ago to recognize Dr. McDonald's leadership in research. And that achievement helped lay the foundation for the McDonald Institute, which continues to unite researchers from coast to coast and beyond, fostering collaborations that are driving Canada's global reputation in astroparticle and fundamental physics. This leadership extends beyond discovery. It inspires innovation, it supports advanced technologies, and it attracts exceptional talent to Canada and to Queen's. I want to pause to extend my deepest thanks to our federal partners for their continued investment in fundamental research. That support at the federal level ensures Canadian scientists can ask the biggest questions and pursue answers to the greatest challenges, answers that will transform our understanding of the world and the universe in time. And this latest investment in the McDonald Institute strengthens Canada's capacity for discovery, and it is an indication of the confidence our country places in Queen's and in our partners to lead at the frontiers of science, decoding the cosmos and illuminating the unknown. So as we celebrate these achievements, we must also look forward. The work we do today lays the foundation for the next century of exploration at Queen's and across Canada. The discoveries made here will continue to inspire, to challenge us, and to demonstrate the extraordinary things that can happen when research is valued, supported, and shared. So congratulations to Dr. McDonald, Dr. Nobel, and our research partners whose dedication and vision have brought us to this moment. Thank you also to our partners, supporters, and today specifically the team that organized this wonderful event, and all of those in the university and beyond who believe in the transformative power of research. Together, we are building on a legacy of excellence that will carry Queen's and Canada into the next century of discovery. Thank you very much. It is now my honor to introduce a very special guest and a good friend of Queen's to speak. Please join me in welcoming Dr. Alejandro Adem, President of the Natural Sciences and Engineering Council of Canada, to the stage. Alejandro.
Thank you very much. It's a real honor and pleasure to be here at such a great university for this momentous occasion. So NSERC is how we're called, Natural Sciences and Engineering Research Council, has a vision to make Canada a country of discoverers and innovators. And the McDonald Institute is one of the greatest contributors to that goal. However, its impact goes back much further to the 1980s, when Dr. Arthur McDonald and his colleagues transformed their vision of a massive underground neutrino detector into reality and propelled Canada to the forefront of astrophysics research worldwide. It is perhaps most impressive that the result of this tremendous collaboration was not to exploit a resource or build a shipping route or erect a monument. It was to help answer one of the most fundamental questions in science and in life. What is the universe made of? 4 decades later, SNOLAB remains a jewel of Canadian research facilities and a source of remarkable scientific and engineering breakthroughs. Its stature was enshrined when Dr. McDonald and his colleagues were awarded the 2015 Nobel Prize for Physics in recognition of their breakthrough discovery of neutrino oscillations and mass observed deep within SNOLAB's detector. And myself and my role at NSERC, when I'm asked, well, what have we done lately in science? I point to art. Nobel Prize winner, and in fact, Canada has won 3 Nobel Prizes in physics over the past 10 years. So we have a proud tradition in this discipline, which goes to the heart of who we are as humans and what the universe is all about. Today, we celebrate a collaboration that is once again pushing Canada's astrophysics community to new frontiers. As President of the Natural Sciences and Engineering Research Council of Canada, it is my pleasure to recognize the Government of Canada's $45.5 million investment over 5 years in the Arthur B. McDonald Canadian Astroparticle Physics Research Institute. Congratulations. And I want to extend my congratulations to the director, Tony Nobel, who will be spending that money, I believe. This investment, announced in Budget 2024, reflects Canada's strong and ongoing commitment to fundamental science. Headquartered here at Queen's, the McDonald Institute connects researchers across the country who are pushing the boundaries of discovery in astroparticle physics. NSERC is proud to help administer this funding and to support the partnerships that make this work possible. Arthur McDonald has continually transformed his achievements into opportunities for colleagues and pathways to empower the next generation of researchers who will carry forward the quest to decode the universe's mysteries. The launch of the McDonald Institute marked a bold new chapter for Canadian astrophysics, fostering deep collaboration, innovation, and training. NSERC is proud to support the Institute and shares its vision to be a globally recognized center for research and learning. Congratulations on the milestones achieved here at Queen's University and SNOLAB, and on a bright future for Canadian research. Thank you very much.
Thank you so very much, Alejandro. Thank you for being such a great partner to the university, for that foundational investment, and for your ongoing work together with us. This $45.5 million announced for the McDonald Institute not only underscores the government's recognition of Queen's and Canadian leadership in astroparticle physics, but also reflects a broader national vision. Investing in discovery fuels innovation, strengthens our knowledge economy, and contributes to contributes to our Canadian technological sovereignty. The impact of such investment stretches far beyond our labs and lecture halls. It supports the creation of technologies. It fosters global partnerships and empowers the hundreds of researchers who have trained at SNOLAB and at the McDonald Institute, many of whom now contribute to science advances and leadership in diverse sectors worldwide. I've spent a fair amount of time with physicists since coming to Queen's. I've witnessed the awareness of the collaboration required across institutions, across borders, in order to accomplish very big things. This is possible. This community of physicists provides an example of how to come together to solve big problems. This is an example that is particularly useful and poignant for the times we live in. Before I invite our next speaker, we have a short video message from our Member of Parliament, Mark Gerritsen. He shares his congratulations on this major investment and milestone anniversary.
Hello everyone, Mark Gerritsen, Member of Parliament for Kingston and the Islands here. And it is my pleasure to greet all of you gathered today to celebrate two remarkable milestones. First, the 10th anniversary of Dr. Art McDonald's Nobel Prize in Physics. And second, a major funding announcement for the McDonald Institute in the 2024 federal budget. Dr. McDonald's groundbreaking work not only reshaped our understanding of the universe, but it also put Kingston and Canada on the global map for scientific excellence. His legacy continues to inspire generations of researchers and students. This is why our government is so proud to support the McDonald Institute, providing $45.5 million in funding over the next 5 years. This funding ensures Canada remains at the forefront of astroparticle physics, driving innovation, discovery, and opportunity right here in Kingston. So congratulations to everyone involved. Your work is shaping the future, and we're proud to support it.
I'd also like to acknowledge the office of Dr. Ted Hsu, who's our Member of Provincial Parliament, who's also here today. So really nice representation. So building on the message from Mark Gerritsen, I'd like to invite Tony Nobel to the stage. He's the scientific director of the McDonald Institute. And so you're in for some very good science content over the next few minutes.
Well, thank you. It's really great to be here. It's a beautiful day, and I wanted to share with you just a few thoughts. Let's get this going. I wanted to start, though, and we've just heard the announcement to the $45.5 million. This is really going to inject a lot of life into the country in terms of what we can accomplish with the McDonald Institute. So I wanted to start by a few words of thank you. And so where I'll start, in fact, is this wasn't easy to get to this point. $45.5 million is not a small amount of money, and it really brought together a number of different factions that really worked hard to make this a success. And I'll start with the Government of Canada. We began several years before 2024 working with the government to try and put together a package that would support this science going forward. It's, we spent many hours in Ottawa, and the approach was really one of, let's figure it out. What could we do? What could the government support realistically, rolling up their sleeves and talking to us, understanding what would be required to make this really successful. So I'm really delighted with the interactions that we had with the government and their support for fundamental science and the, elbows up, let's make it happen in Canada. It was just wonderful. We also have been working for many years with the funding agencies. So we just heard the announcement from Alessandro just now about the actual $45.5 million, but there's a long, long history of cooperation and working with NSERC and also, pardon me, with CFI, who have a different role in terms of supporting the capital costs of the experiments that go in, and then the provinces that partner with the CFI. But right from the very beginning, when we were developing SNOLAB, there was no mechanism really to fund the operations. We got money to build the lab, but now how do you operate that? And again, we sat down with NSERC. We had all kinds of arrangements that they found ways to support us because they had confidence in the science that was going to come out of the facility. And so we have a long history of cooperation, working with the funding agencies, working with the government to make things happen, and it really has. I came here in 2002, and so my experience is shorter than Art's, but what I have observed is completely unwavering support from Queen's over that entire period. The support from all levels, from the department, from the Faculty of Arts and Science, from the Faculty of Engineering, and of course in the VPR's office. And again, it's been this very pragmatic approach of, this is exciting, we'd like to find some way to support you, how can we do that to make it successful? And so all across of these sort of pillars of support, there's been great collaboration and enthusiasm and pragmatism to make this happen. And what does that actually fund when you put that all together? What we've talked about today is the money that's going to support the McDonald Institute, which is primarily this university-based research and development. But that's not the whole story. We all know about the fabulous facility we have, SNOLAB, which is where many of the experiments that we are supporting are housed. So the SNOLAB needs to be supported. The research that happens at the university is what generates the ideas, creates new experiments, new ideas, and that eventually mature into something that's going to be feasible, and more likely than not will end up at SNOLAB. And those complex experiments that have now been designed and invented also need support, because many of those experiments are extremely large. When you see the pictures of snow, in fact, this is a very interesting picture of the Snow Plus, the successor to SNOW. These are things that are the size of a 10-story building with volumes that are measured in thousands of tons of this or that. These are big, complex experiments at the cutting edge of technology and science, and it really needs an awful lot of support, and you really need to support this entire portfolio to have success. I also wanted to point out that this, although we are hosted at Queen's University, this is a partnership that goes all across Canada. And so on this map you see Queen's, but we also, as I mentioned, we have the premier facility in the world, which is SNOLAB. And I'm particularly delighted that Jody Cooley is here today. Jody is the executive director of SNOLAB, and there really is a very tight connection between what we're trying to do in terms of the research and development and the support we get from the facility that really is the best in the world. But that's not all. We're trying to support we have a number of world-class facilities across Canada, including Triumph and Ocean Networks, where our research benefits from those facilities as well. But the real partnership comes in all of the universities that are involved in the McDonald Institute. So at the moment, there are 10 different universities. These are the red stars, which you see more or less across Canada, are all involved in a very deep and profound way in supporting what we do with the McDonald Institute. And there are 6 institutes as well, and those are the ones in the blue diamonds. But that's not all we support. Those are people who are, if you like, official members of the McDonald Institute, but there are researchers all across Canada who have benefited from us where we support various activities, and so I refer to them as our collaborators on this project, but a very large number of universities and partners. The science, I can't get away without saying a little bit about the science. And Melinda's getting nervous now. But okay, so it's the science of astroparticle physics. So what is astroparticle physics? So to me, my background is in sort of collider physics, particles. I'm trying to understand what are the properties of the most fundamental building blocks of nature. So we're talking about neutrinos a lot, dark matter, but particle physicists are looking at the complete picture of all the particles in the universe and trying to understand what they are and how they interact. So that's particle physics, so that's part of the name. On the other hand, many of those particles come from outer space. There are black hole mergers, there are supernova explosions, there's things that are spewing out particles all the time, accelerating them. And it really is fascinating that we can use those particles when they arrive at Earth to understand what's happening at the sources. So this is the realm of astronomy, trying to understand the properties of those celestial objects. When you put that together, so you've got particle physics, and now we understand the fundamental building blocks, we understand the sources out there in the universe, and that allows us to start studying the history and the evolution of the universe, and so that's the cosmology. And so astroparticle physics is really an intersection of particle physics, astronomy, and cosmology, understanding everything we can about the origins and the evolution of the universe and its contents. What we do in terms of our priority areas in physics is, well, exploring the origins of these matter. So I have up here two different pictures. One is a sort of artistic conception of how dark matter might be distributed around in the universe, and I'm told don't hit that button. So it's actually a little bit embarrassing that when I go to bed at night and I tell my students we know everything about the universe, from 10 to the minus 43 seconds on, we can predict more or less everything that we see in the universe. The problem is what we can see in the universe is actually a very small part of the universe. And 85% of the matter, everything that we see in here and so on, is unknown, right? We represent only the 15%. And if we talk about dark energy as well, we understand about 5% of the universe. And as a practicing physicist, that's a bit embarrassing. In terms of the fundamental neutrino properties, okay, this started with the observations that were made that have been talked about, where we understood that neutrinos are changing in flavor as they travel from the sun. They're only made as one type in the sun. When they arrive here, they're a mixture. I often explain to my students, you know, if you were in the field and you saw an apple fall off the tree, and when it hit the ground, it was a banana, you'd be a little surprised. And we were. But there are other big questions around neutrinos. Neutrinos are so hard to detect, it's very difficult to measure their properties. So we still don't know what is the mass of the neutrino. We know there are 3 neutrinos. We know they must have a mass because the process that we saw, that they changed flavor, dictates that they have a mass. But we don't know what it is. We don't know why we live in a universe which is made completely, more or less, of matter. We can make antimatter in the lab. We see it in the cosmic rays, but it's a very small fraction of the universe. And yet at the beginning, one would presume that they would be made in equal amounts. And it turns out again that the neutrino might be the secret to understanding why we live in such a strange universe. We can also build on the neutrino oscillation story and now make detectors that do much more advanced measurements by taking so this is an example where I will be next week actually, but this is Hyper-K in Japan, where they're building a new detector where they will send a beam of neutrinos from one side of Japan, from an accelerator, 295 kilometers, to a detector underneath a mountain on the other side of Japan. And by doing that, they will be able to really probe in depth some of the properties of neutrinos. So this is all very exciting, and so these are the things we are supporting with the McDonald Institute. We are also branching out into some new areas, including multi-messenger physics. So this is where we have particles that are coming from way out in the galaxy that are arriving at Earth, and we're learning about, again, the sources and so on. So this is a plan for a neutrino astronomy experiment called P1, where neutrinos will actually interact in the water. That's the detector, produce flashes of light. So your job is actually to put detectors in the water. And this would be a cubic kilometer array of detectors that are measuring the properties of neutrinos coming from outer space using a very deep, clean spot well, this is waters just off the coast of Vancouver Island, so very Canadian. And that's an experiment that's just getting going and holds a lot of promise. And it benefits greatly from the fact that this infrastructure here is already laid out. This is from Ocean Networks Canada, where they're doing other oceanographic measurements, but they have power, they have fiber optics, it's already 2 kilometers underwater, and we can connect into that with a new detector. We're also getting involved in gravitational wave astronomy, so looking, there's been a huge explosion of activity in terms of understanding what's happening with black hole mergers, with neutron star mergers. We now understand that most of the components in your body, if you look at the gold and so on, well, maybe we're not all full of gold, but even with 45.5 million. But those elements were made in black hole mergers. And so parts of your body were previously inside a black hole that merged with another black hole and spewed out all these materials, including parts of you. So it's fascinating to understand. So these are areas that we're expanding. And so we have this legacy that started with the initial SNO experiment. And the growth in this field has been tremendous, and it will continue to grow thanks to the funding that we have just received through NSERC, but the program that we call the NSERC MRS. And so what is that going to do? Well, it's going to inject a lot of activity into the local economy. This is a picture of a device that's being developed by our colleagues and partners at Sherbrooke for silicon photomultipliers, which they are excited about because it could modernize and revolutionize the way you do positron emission tomography for scanning, medical imaging, with much lower doses required for the patient and so on. But it's the same detector that we need to increase our sensitivity. So working together on different themes, but together. We're also going to have a focus on students. Again, as we have supported over 400 students in the last few years to get their masters and PhDs and postdoctoral positions and so on. And we have a major education and outreach program as well. And I just love this picture of the fascination of these children on learning a little bit about the NEWS-G dark matter detector. And so that brings me to the last item. So this money will help to launch Canada really onto the global stage as leaders in the science, as researchers, and as hosts through the SNOLAB facility. The original SNOLAB facility was built through a special program at CFI to invite international scientists to come to Canada to do the research with Canadian scientists, and I think that has been very successful. And as you will hear, a large part of that has been building on the successes we have had along the way. And so now it's my pleasure to be able to welcome Art McDonald to the stage. So Art, I have known, actually he won't know this, but I met him in the 80s when I was doing a tour of Princeton University and he was still there. But I've known him and worked very closely with him since I came back to Canada to work on SNO in 1994. So Art, as you probably know, was born in Sydney, Cape Breton, Nova Scotia. And if you don't have quite a reference for that, it's about a 6-hour drive east of Fredericton, New Brunswick. Art then stayed in Nova Scotia and attended Dalhousie and got his bachelor's and master's in Dalhousie before going to Caltech, where he got his PhD. Spent some time at AECL as a research scientist before going to Princeton. And then we were so lucky to be able to capture Art from Princeton as the SNO experiment was starting to come together, to come to Canada as the director, provide the leadership that was necessary to pull the community together and to deliver. And so without further ado, I'll invite Art McDonald to come and say a few words and, of course, congratulate him on 10 years since that fateful day when you were woken up at 6 o'clock in the morning to learn that you've got the Nobel Prize.
So you just heard from the heart and soul of the McDonald Institute. Tony's creation, Tony's development, all of what has been done so far and will be done in the future is due to Tony. They put my name on it in order to hearken back to the success of the SNO collaboration back in 2001, 2002, that led to the Nobel Prize. I represent them as the Nobel laureate in the same way as I, due to the naming, represent the McDonald Institute. But Tony is the person who created it and who is, as I say, the heart and soul. And you also just learned why it is that Tony, in spite of all his duties, not only as the director of the Institute, but also as a leader of one of the dark matter experiments, PICO, still twice was designated by the students as the top professor in particularly first year engineering physics here at Queen's. The engaging way in which he presents things was recognized by the students as well. So another round of applause. It's really been my pleasure to work with Tony for many years. Tony actually was also the second director of the SNOLAB facility, turning it into operations at that point in the activity there. And again, we're very pleased to have Jody here. The collaboration with Jody and with SNOLAB is very important to us as we go forward, because really what we have is a laboratory which is, as Tony said, a premier laboratory in the world. And what the McDonald Institute is attempting to do is to provide the support for university researchers who can develop the experiments with help from SNOLAB in terms of providing a location for development work and eventually full-scale work on these experiments, and support to the university laboratories to make it possible for the scale that's necessary for these experiments to take place, to occur. An example of the scale of these experiments is what you see on the right there, which is actually a picture of the inside of the Sudbury neutrino, or SNO, experiment. It's in a cavity that is, well, imagine the size of this stage extended up for 10 stories. That's the cavity in which that occupies about 2/3 of the space in the middle of it. That's the scale of what we're doing there. Now, what I've been asked to do today is to talk about what has happened since the original measurement by the Sudbury Neutrino Observatory of neutrinos from the sun. And that's what's happened. What you see here is the two experiments, the SNO experiment and the Super Kamiokande experiment in Japan, where my colleague Takeaki Kajita led the Super Kamiokande collaboration in measurements of neutrinos produced in the atmosphere, whereas we studied neutrinos coming from the sun. But in a sense, we were able to define where you should look, because there had been previous attempts, and the properties of neutrinos really were essentially unknown, other than the fact that it was thought they had a zero rest mass and always traveled at the speed of light, which we were able to show in both experiments is not true. Since we know roughly where to look, you see the large number of experiments around the world that are studying neutrinos. And I have to say, you'll see, if I had the plot, a similar growth in work on dark matter measurements, and we'll talk about dark matter later, once we determined that neutrinos, in fact, are not the dark matter particles that make up such a large fraction of our universe, as Tony said. So that's been the impact internationally, and there are a number of experiments that people here at the McDonald Institute are involved in, associated with the work on studying neutrinos. And in particular, what Tony pointed out is the Hyper Kamiokande experiment which is in Japan. Their major highest energy accelerator is essentially entirely devoted to neutrinos, as is the highest energy accelerator in the United States at Fermilab. So it really has transformed the field of particle physics to have a substantial component of neutrino physics, but in addition, a substantial component of astroparticle physics. And we're very, very lucky to have had the work that Tony did to create the the CFREF, Canada First Research Excellence Fund, creation of the McDonald Institute prior to the extension we have today, so that Canada, through SNOLAB, where we can do a number of measurements that are of a fundamental nature, and also here at and across the country with the McDonald Institute supporting such work. But what the heck are neutrinos anyway? They are not a breakfast cereal. But it turns out that they are one of the three types of particles that we can't subdivide any further, at least as far as we know today, and scientists always say as far as we know today. Quarks and electrons, or particles like them, there are actually three other rows like this in the full standard model, are the other particles we don't know how to subdivide further. Quarks make up neutrons and protons. They have 1/3 charge, and you can make either neutral or +1 particles. And those are what is in the nucleus of atoms. And around that nucleus, there are various numbers of electrons. Same number as there are protons, because it's all overall electrically neutral. And that is the chemistry. And that is the way this world that we're all familiar with works, is the interaction of electrons going around atoms with other things. Now, neutrinos are very unusual particles. They only interact by the weakest of the forces, and therefore they can travel through an amount of lead corresponding to a light year, or a travel for 1 year of a particle of light. It's about 100 billion, pardon me, 1 billion kilometers of lead, with only a 50% probability of stopping. In fact, there are a heck of a lot produced in the sun. If you hold out your thumbnail, there's about 5 million per second going through the equivalent square centimeter of your body every second. But only once in your lifetime will one neutrino perhaps transform one atom in your body into something else, and you won't even notice it unless it happens that it hits you in the eye, and your eye happens to be closed, as many eyes are by the time I get to this point in most talks I've given. Then you might see a faint burst of light. And that is what we used basically in the Sudbury Neutrino Observatory to observe these neutrinos. And because they do interact occasionally with matter, but in order to see one an hour, we had to build a detector the size of a 10-story building, as I mentioned. And the discovery we made is that the type of neutrinos that are produced in the sun, as Tony said, change into one of the other two flavors, so-called, before they reach the Earth. And that is a major discovery. In order to do it, we had to build this enormous detector. You can see the person here. That's to scale. Imagine a 10-story building situated 4 CN towers underground, built in ultra-clean conditions, filled with $300 million worth of heavy water in the center here, such that that burst of light could then be detected by light sensors. That's pretty good leverage in any market. Dave, would you agree? Dave is the chairman of our Board of Trustees, and it's a real pleasure to have him here today. The construction itself was a major engineering feat, and you'll notice in the name of the department, we have physics, engineering, physics, and astronomy. Perfect combination of people here at Queen's at the time to be able to tackle a job of this nature. You can see the scale of people and the fact that everybody's in ultra clean clothing. It's a class 2000 condition throughout the detector when we were building it. And so what we observed is that the type of neutrinos produced in the sun, before they reached our detector, they had transformed from 100% electron neutrinos to 2/3 of them being represented by mu1 or tau neutrinos. We could tell this because with the heavy water we had different signals in our detectors. And so the standard model of elementary particles had to be changed, and that's what the Nobel Prize was awarded for. But there were also quite practical things that came from this. First one is less practical, but very interesting, and starts this tale of how existential what our measurements tend to be. And that is, we were able to show that the calculations of how the sun burns are really very accurate. And it's in stars like our sun that the elements carbon, nitrogen, and oxygen that are such an important part of our being are created. And so it's often said that we are made of stardust. This is at least one example where that is the case. But understanding in detail how those calculations are accurate, and we were able to confirm them full scale in a plasma confined by gravity, is very valuable, because here on Earth we're attempting to do the same sort of thing in developing what's called fusion power. It's fusion nuclear reactors fusing together light nuclei that powers the sun. It's what we're trying to harness here in fusion power reactors. The calculations are very similar, and we've been able to verify them full scale. And so that sort of practical spin-off is something that happens often in this process of attempting to understand as much as you can about the world by studying physics on a variety of topics. And so all of that led to this, which, as Tony mentioned, it was actually 5:15 a.m. that they called Tony. This is where Janet and I ended up experiencing things. That was October the 6th, 2015, and December the 10th, 2015, we were in Stockholm, and that's the 1,500-person banquet that we attended, and so a number of my family who are here today were also there. I don't think you can figure which one you are. You see yourself, Heather? Good. But what was wonderful is that we were able, I was told by somebody else that if you really finagle a little bit, you can get more than the 14 people you're allocated to bring to Stockholm. And people were able to share events when they came. And so we got a total of 35 people, including spouses, who are a very important part, as I know very well, in all of this exercise, who were collaborators on the snow experiment, because really, as I say, I represent them in terms of this accomplishment. And that was wonderful. It was an experience that was just a highlight of our life. But there are challenges that come along with it, such as, you saw those stairs. I think there's 70 of those stairs. I had to come down those stairs beside the Crown Princess of Sweden, who had a dress that went all the way to the floor and was 6 months pregnant at the time. I'm looking down, and that's because I didn't look up from the start to the end. And so, indeed, there was a challenge. But, you know, I get asked by students, what should I do to win a Nobel Prize? And the answer is, you don't attempt to win a Nobel Prize. You attempt to do good science, and you find very good collaborators and work with them. And the reason you want to do good science is because you're inspired by things that can be, in fact, quite existential in their nature. This Big Bang theory has been developed over roughly the last 60 years. And one of the people who was a central person in developing it is a good friend, Jim Peebles, who's a professor at Princeton and was there when I was there. But he's from St. Boniface, Manitoba. And he won the Nobel Prize a few years ago for being the driving force that has put this together. He's a theorist, but there's an enormous number of measurements that have been made in astronomy and in astroparticle physics that put together a theory which seems to hold together very well. Still a number of unknowns in it, which we are studying, but the idea is that 13.6 billion years ago, there was an enormous amount of energy converted into equal amounts of matter and antimatter from these various particles. The basic ones we know are quarks, electrons, and neutrinos. They were created by energy being converted into matter and antimatter in the same way that in positron emission tomography, you have an electron and an antimatter equivalent called a positron that comes together and makes energy back-to-back gamma rays, which are what's used in positron emission tomography, by putting detectors around your head and looking for where the gamma rays are in coincidence and drawing lines in between them, except these days the attempt is to use new generation of silicon photomultipliers, of which we're very actively involved in the development, particularly University of Sherbrooke, supported by the McDonald Institute, where you attempt to also measure the timing across to improve the resolution. So that's matter and antimatter. That was produced in enormous numbers many, many years ago, as you can see, and at very high temperatures. Following this explosion, it appears as though the universe has continued to expand and cool off. And as it cools off, various things happen. First of all, quarks come together to form neutrons and protons. They come together to form the nucleus of atoms, hydrogen and helium in the early stages. In fact, one of the reasons we know that this is a very credible theory is that the amount of hydrogen, helium, and other light elements that we measure in our universe today fits exactly with the theory as to how this could have occurred in this process that Jim Peebles and others worked on. By the time you get to 300,000 years, the electrons have combined to produce neutral atoms, and at that point, the light from this enormous Big Bang begins to shine through, and astronomers have done really exquisite measurements to tell you that, in fact, this theory has validity. And then after about 1 billion years, and by the way, that would be 12 billion years ago, the reason why the James Webb Space Telescope is particularly significant is that it's the first one that can go back 12 billion years, and therefore go back to the point where the first stars were being produced. So astronomers are making progress. We're making progress in a variety of ways. And of course, after the formation of the stars and galaxies, the sun is formed, planets go around it. The sun and other stars are the generation of the elements that form the possibility of light on our planet. And so this is existential in the sense not only of how life has formed on this planet, how humans have formed from that, but also how has everything formed. This is what the philosophers were trying to do back in the Greek days, of understanding our world in detail. And therefore, this is the sort of thing that attracts students substantially to this area. It really is existential questions we're trying to answer. One of them is, what is the so-called dark matter that is apparently influencing the formation of galaxies and at this point in the evolution? We know there is about 5 times as much mass in the spaces between the stars when you look out on a starry night. When you do that, you're going to see, you're looking through what looks like kind of a cinnamon roll. You're looking through the cinnamon roll along one of its edges. But it turns out that if you look at similar things, the stars are moving so fast in that outer region that they would have flown off into space if there wasn't 5 times as much gravitational attraction from something that isn't glowing. And that actually is borne out by other measurements across the universe. And dark matter is, according to one model, one of the things that it's worth looking for, and we're very fortunate that SNOLAB gives us that opportunity. The other question is, where's all that antimatter? Why don't we have gamma rays being produced by lots of positrons left in our universe, for example, and creating the equivalent amount of as we have matter? And the answer is something caused it, the antimatter, to decay away since the original universe creation. And the current theory, has the most acceptance, is that neutrinos are responsible for that. In order to study one element of it, we have developed the SNO Plus experiment, which is a gigantic recycling job on the SNO experiment, replacing the heavy water with liquid scintillator that produces about 100 times as much light. And the other thing that's being looked for is at these experiments like Hyperkamiokande, where they shoot a beam of muon neutrinos and another beam of muon antineutrinos, and they look at the difference in the properties of neutrinos and antineutrinos to look for differences that fit into the theory of how the antimatter has decayed away. So we're very fortunate to have SNOLAB, directed by Jody, as a tremendous resource for the sort of experiments we're doing. You can see here, this is the area where the SNO experiment was in the first place, but starting in 2002, it was expanded, and starting in around 2010 or so, it went into operation. And what we're finding is that this lab that was built to bring people from other countries to come and work with Canadians is very, very successful at doing that. These are the set of experiments that are in place, and we still have room for another large-scale project here. But you can see dark matter, lowest radioactivity location in the world, and therefore what we're doing is putting a variety of different materials, each of them having a little trick as to how you can get rid of other background. But you see fluorine, silicon, argon, helium as experiments that are looking for dark matter, well, for us to run into the dark matter that is between the stars in our galaxy and get a signal. And we have some of the most sensitive experiments in the world to do that, including the SuperCDMS experiment, which is a 60 million experiment, which is a US, Canada, and international collaboration, which is, I heard, just about to cool down. Have they started, Jody?
They have done some cooling.
They've already started cooling. It's very current, and we're really going to be excited over the next year or so to see the results of that. So we're very fortunate to have SNOLAB as a place to do our work, and you can see it's very clean everywhere. This is Stephen Hawking, who visited in 2012, very interested in seeing everything, and very inspirational individual who would take 2 or 3 minutes to form even one sentence when he would ask a question from our students when he visited. But a great mind and an amazing person. The interesting thing about Stephen Hawking is that all of his good work was done after he had his disability. And that's what makes him so inspirational. But we also have, as I said, spin-offs from this, which include improvements in positron emission tomography. At the time of the COVID crisis, we downed tools on dark matter work, and combination of our academic people and people from national labs across the country, and also people from Italy and really across the world, got together to build a low-cost ventilator, and also easy to supply, and we published it in the open literature within about 4 months of March 2020, when the original pandemic began. But this is in addition to the main thing that we do, which is to train individuals in science and technology such that they end up in jobs of value to Canada. We did a survey of our SNO 200 scientists and postdocs as to where they were and what they were doing 10 years after we stopped taking data. 25% of them were academic professors in very good places, including Berkeley and Oxford. But 75% of them were working for companies like JP Morgan, banks, leaders of research laboratories. Some of them had started their own companies. They were doing things that were not specifically astroparticle physics. But from our perspective, they had learned evidence-based decision-making and were carrying it to whatever industry or job that they took after they finished their graduate work. And so we regard ourselves as a principal supplier of highly qualified personnel for this country, and we're very proud to be doing that. And this is, I think, valuable for companies who are attempting to survey the world, if they're going to build the latest in technology, to be able to understand that that thing that happened in Germany or Japan, which is a new development, is significant or not. Should your company, in fact, move in that direction? And so basic science is an important component, both from the intellectual point of view and also from the industrial point of view for Canada. So, there, final slide, which is me to be able to say thank you both to Queen's University, to SNOLAB and the way that they have been providing wonderful support to us, and also to Tony and the McDonald Institute for what they're doing to continue this activity from now on. Thank you very much. So now it's my great privilege to introduce to you some of the next generation. This is Julie and Zoe, who are going to tell you a little bit about their experience in working here at Queen's as one of the institutions in our cross-Canada McDonald Institute. And I don't know what they're going to say. I hope it's okay.
So hello, my name is Julia.
And I'm Zoe.
So it is such an honor to be invited here to share my experience in the research community and my thoughts for the future. So you may be wondering what I might be able to add to today's celebrations, as my studies in astroparticle physics thus far have been a brief history in time. I first learned about neutrinos when Dr. McDonald actually visited my high school to share his research and a glimpse into the world of astroparticle physics. This meaningful outreach experience started me on the path I'm on today, where this past summer I actually contributed to neutrino research. I chose to study at Queen's because of the inspiring, groundbreaking research in this field. Now, I do not naively attribute all good things to one person or one award, but it seems to me that curiosity feeds curiosity, striving for excellence drives excellence, and nurturing community fosters our humanity. It does not go unnoticed that acts of community are a priority. I have been so fortunate to see this community in action, specifically at the McDonald Institute National Meeting this past summer. Over coffee breaks, late-night dinners, and collaborative discussions of our work, I befriended many undergrads and young graduate students. Our excitement was palpable over discussing, contributing to learning more about the universe and the possibilities of creating more knowledge. 20-year-olds passionately discussing physics while meeting leaders in the field who shared their wisdom, funny stories, and drive for research. As students and young researchers, we are eager, and thanks to the continued support for the McDonald Institute, we are empowered. Thank you to the community, the government, and those who fund this work. I will now hand this over to Zoe.
Thank you, Julia. I'm Zoe, and I promise I'm one of the last things between you and donuts and coffee. 5 more minutes, then Nancy's going to come up and release us all into the wild. I'm a PhD student here at Queen's, and I consider myself extraordinarily fortunate to have ended up here. You could not have told me that this is where I'd be. I did my undergraduate in pure physics, and had no inkling that I was going to go into astrophysics until in my 3rd year there was a McDonald Institute-led initiative, CAPS, the Canadian Astroparticle Physics Summer School. And I heard about it, I applied, I jumped on a train to Kingston, and I met Mark Richardson, the associate director, who showed me this incredible warmth, this strength of character, and this sense of community that I did not expect to see in this level of education. And I decided to come to Queen's because, you know, I fell in love with neutrinos over the course of that week, but I also fell in love with this incredible sense of community that I saw here, because it's not just between all of these incredible institutions, but also here locally at Queen's, this community is so incredible. And this seems like such a trivial example, but we have lunch together twice a week. All the astroparticle groups, they come together in a room, and the Institute feeds us, and we get up and we talk about our challenges and our accomplishments, and we share everything that's going on with our experiments. And I just think that's amazing, and it's so indicative of where the focus is here. It's about the community. And it makes me a better physicist. It makes me more comfortable bouncing ideas off each other. It makes it so that I can walk down the hallway and knock on an incredibly talented physicist's door and say, "Oh, hi, I saw your fitting function for the single photoelectron peaks on your photomultiplier tubes." And they'll share that with me. And yes, that jargon is as difficult as it sounds for a first-year PhD student. But yeah, I'm not nervous to do that because of this openness and this sense of community that you don't expect to see in the sciences, because the sciences are typically very competitive. You know, it's this world of publish or perish, and it seems like there's this little oasis of collaboration here, and that might be the naivety of grad school talking. But I am so grateful, because I think one of the greatest adversaries of my imposter syndrome, for example, is having this horde of people behind you, encouraging you. It's so much more difficult to say you're not worthy when you have all of these people telling you that you are. So I like coming to work every day, which is wild. I love being able to volunteer in all of these outreach positions, because I love being a part of cultivating that community. So I would just like to say thank you. Thank you, Mark Richardson, for being the beating heart and just such an important part of us coming together. Thank you, Tony, for your awful sense of humor. Thank you, Art, for your kindness and your advice and your tireless leadership. Thank you, Queens, for allowing us all to be here, and I'm very grateful. It's not only does this funding foster, direct research, but it also creates this community that allows us to be really successful scientists, and this network that I'm becoming a part of gives me this confidence that I don't know what my next step in life is, but I feel like I can do whatever I can dream of. So, thank you.
Thank you.
Wow, another one. So let's reflect on the comments today. We celebrate the remarkable journey since art and the Sudbury neutrino collaboration were awarded the Nobel Prize 10 years ago. Their discovery not only transformed our understanding of the universe, but also ignited a legacy of curiosity, collaboration, and excellence here at Queen's and across Canada. Canada is a physics nation. We also heard from Dr. Tony Nobel, who spoke so eloquently about the McDonald Institute's leadership as Canada's National Physics Network, working closely with world-class research facilities like SNOLAB. The McDonald Institute is poised to fuel the next generation of discoveries in physics, discoveries that will deepen our understanding of the cosmos and expand the horizons of science. And from Julia and Zoe, talented representatives of the next generation of scientific researchers, we were reminded why we must continue to ask bold questions and push the boundaries of science and knowledge. Their passion, their optimism embody the future of Canadian science, a future that depends on sustained investment, partnerships, and a welcoming community committed to discovery. All of that together makes magic happen. Today's celebration is made possible by the vision and generosity of government partners, dedicated research collaborators, our proud alum, and each community member present. So on behalf of Queen's University and the McDonald Institute, thank you. Thank you for joining us to mark these significant milestones. Now, some fun and some relaxation. I invite you all to continue the celebration by enjoying the reception in the atrium. I am told there are some Cosmos-themed refreshments. There are displays. I believe there's a Nobel Prize itself, which it must be a tremendous photo opportunity for everyone here. Engage with some of the interactive exhibits that will be outside, and some of those will sort of introduce even more around astroparticle physics, because you've got your appetites whet from this morning's conversation. So from here, let's continue our spirit of discovery, wonder, and learning, knowing that by investing in science, we invest in the betterment of humanity and the possibilities that lie ahead. Thank you. Enjoy the rest of the morning.